Hello, this is video number 1 of section 7.2, and so this is the penultimate section of the course. After this we'll have just section 7.4 left, and then I will have taught you everything I planned to teach you about linear algebra. So, up until this point in the course, we have looked at matrix equations that were linear. Right? So of the form AX equals B, for example. But those aren't the only types of matrix equations out there. And in fact, looking at some nonlinear matrix equations, these types of equations are very useful in applications to a variety of things. And so this section, we're actually going to see a different type of matrix equation, which, as we'll see, produces a quadratic equation in terms of the variables, meaning we're going to have some squared terms. So, leads us to our first definition, a quadratic form on Rn. So this is a function on a vector of length n, is a function q of x, where again x is a vector of length n, such that q of x is equal to x transpose times a times x, where A is an n by n symmetric matrix called the matrix of the quadratic form. So the types of functions we're going to be studying are functions on quadratic matrices, or not quadratic matrices, symmetric matrices, which remember we studied in section 7.1. So what do these look like? So first I just want to look at a couple quadratic forms defined by 2x2 matrices. So we're going to let x be this vector x1, x2, where here x1 and x2 are variables. And we're going to see when we expand this expression in terms of a and this vector x, what does this quadratic form look like? So we want to expand the expression x transpose times a times x, which when we write everything out, this is the sideways vector x1, x2, times the matrix 2, 0, 0, negative 2, times the vertical vector x1, x2. Now you can do this multiplication really in any order you want. So first I'll multiply these two together. In doing so you get the vector 2x1, negative 2x2. And so notice then multiplying this horizontal vector times this vertical vector is essentially taking the dot product. And so this would be the quadratic form corresponding to the matrix A. So x transpose times a times x would be the expression 2x1 squared minus 2x2 squared. All right, let's look at a matrix now that doesn't have 0 entries on the off diagonals. So this would be x transpose bx and again this is equal to x1, x2 times the matrix B times x1, x2 All right, so first things first, I'm going to multiply again the right-hand side of this to get a vector. So this should give me negative x1 plus 3x2 and 3x1 plus 4x2. So notice now I get a slightly more complicated vector here in the second step, where now each of these terms contains both, or each of these entries in this vector contain both x1 and x2 terms. It's a linear combination of both. And so multiplying this out, I get negative x1 squared. Notice here in the first entry, the x1 is going to match up with the x2 to give me 3x1, x2. But in the second entry, the x2 is going to match up with the x1 to give me 3x1, x2. So I'll get 6x1, x2 plus 4x2 squared. And so this would be the quadratic form associated with the matrix B. At this point, you might have already started to see kind of a pattern in how maybe we could take a matrix and eliminate a lot of these middle steps to calculate its quadratic form. You kind of might have started to track where these coefficients in the matrix are going, and especially because the matrix is symmetric, it can be relatively easy to track where the coefficients should go. Before talking about the pattern, I want to quickly look at a quadratic form corresponding to a 3x3 matrix, because I think that will really kind of solidify what we eventually want to look at with how to calculate and kind of interpret these quadratic forms without always having to expand the multiplication of vectors and matrices. So we want to do one more example. So this time we're going to let x, and note that normally the vector variable, or the variable vector, won't always be specifically stated like this, but it's just always assumed to be, if it's of length n, x1, x2, x3, all the way up to xn. Those are sort of just the assumed entries in general. And this time we're going to let A be the matrix 1, 0, -2, 0, 2, 5, -2, 5, 3. Make sure that's symmetric. Yes, it is. And so we want to compute the quadratic form with matrix A. So that is Q of x is equal to x transpose times A times x. So this will be a little more involved, like I said, but still definitely doable. So again, we're going to get the horizontal vector here, x1, x2, x3, times the matrix A, times the vertical vector, x1, x2, x3. So again, we'll do horizontal vector last, so x1, x2, x3, times, so now matching this up, this gives me 1 x1 minus 2 x3 in the first entry, 2x2 plus 5x3 in the second entry, and -2 x1 plus 5x2 plus 3x3 in the third entry. And so multiplying this out, I get x1 times x1 minus 2 x3 plus x2 times 2x2 plus 5x3 plus x3 times -2 x1 plus 5x2 plus 3x3. And so expanding all of this and combining like terms, you should get this is equal to x1 squared plus 2x2 squared plus 3x3 squared minus 4x1 x3 plus 10x2 x3. All right, so like I said, at this point, we've found sort of a pattern that we can officially write down now as to how we can go from matrix to quadratic form without having to always do this expansion. So if A is an n by n symmetric matrix, and Q is the quadratic form corresponding to the matrix A, so that is A is the matrix of this quadratic form, then we know that the x sub I squared coefficient, and so this is for each I from 1 to n, is the ith diagonal entry of A. So the x sub I squared coefficient for all of I, all integers I from 1 to n, is the ith diagonal entry of A. Notice here, the coefficients I'm specifically talking about here are these three coefficients attached to the x1 squared, x2 squared, and x3 squared. And so notice the coefficient of x1 squared here is just 1, first diagonal entry. Coefficient of x2 squared is 2, second diagonal entry. 3 is 3, third diagonal entry. So what about these terms? Well, the xi, xj coefficient when I is not equal to j is the sum of the ij and ji entries of A, which are always equal because A is symmetric. So notice here, this -4 comes from adding the row 1, column 3 entry plus the column 1, row 3 entry. And again, since A is symmetric, they both have to be -2. And so you can calculate these two entries by looking at one of the two, or both if you want, and adding them, entries corresponding to these indices in either order, and it'll be the sum. So 10, x2, x3, the row 3, column 2, and the, row 2, column 3, and row 3, column 2 entries are both 5. And notice there is no x1, x2 term because each of those corresponding entries are equal to 0. So knowing this now, we actually also now have the power to work backwards if given the expanded quadratic form first and actually calculate the matrix for the quadratic form. So I want to do one example of that because we know where these entries come from now. We can sort of work our way backwards and calculate the matrix if given the expanded quadratic form. So we're going to let Q of x be the following quadratic form. And so what we want to do, I guess I'll put our goal here. Find the matrix A of the quadratic form. So that is the matrix so that Q of x is equal to x transpose A x. So this is really just a matter of sort of working our way down either the matrix or the quadratic form, whichever order you want to do these in, and just filling in the entries. So maybe I'll do diagonal entries first, right? So the x1 squared term is 2, so that should go in the first diagonal entry. -3 should go in the second diagonal entry. 7 should go in the third. Now I've got an x1, x2 with coefficient 1, which means this should be the sum of the two row 1, column 1, and row 2, column 2, and row 2, column 1 entries. They should be equal and they should sum to the x1, x2 coefficient. So here, each of these entries should be 1/2. x1, x3, that gives me -2 in the two 1, 3, 3, 1 entries. And there's no x2, x3 term, so I put zeros there. So now we can work our way both forwards and backwards in this way when computing the quadratic forms. And we, yeah. So I actually will probably just end this video here, considering what I have after this. It's probably a little longer than I want to make the video. So I'll probably stretch this out to 3 videos, even though I had originally planned for 2. So, yeah. So, as we'll see in video 2, we're eventually going to want to start looking at quadratic forms that don't contain these terms where we're multiplying variables together. Because if you remember looking at the original first matrix we saw, that matrix was diagonal, and we like diagonal matrices for quite a few reasons. Right? Their eigenvalues are easy to calculate, and we'll see some geometrical applications actually of why we want to eliminate these terms in quadratic forms. And so I'll just end. We actually have a name for these terms. So in the quadratic form, q of x, the terms xi times xj, where I is not equal to j, are called cross product. Cross product terms. And like I said, in the next video for this section, we'll talk about how we can take quadratic forms that contain cross product terms and transform them into quadratic forms that do not contain cross product terms.